Hello everybody and welcome to our last video on advanced functions. Today we're actually going to go over everything we've learned throughout this course, every single chapter, and all of the most important concepts that you'll need to know for your final evaluation and or exam. As a quick overview, here are all the chapters we've done this far. So we have done polynomial functions, polynomial equations and inequalities, rational functions, trigonometry, trigonometric functions, exponential and logarithmic functions. We also talked about different strategies for solving exponential and logarithmic equations. And lastly, we talked about how we can combine functions together. Overall, we've covered 8 chapters, but in reality, we really talked about 5 or 4 even different concepts. However, as part of this video, I've decided to show you all of the most essential topics from each of these chapters, even if we do talk about polynomial functions for 2 of them. So let's get started. So first of all, the most important thing you need to know from chapter 1 is the format of a polynomial function, which is this right here. You need to know what this function represents. You need to know how to talk about its order, which again would be the power that it has, the highest power. You would need to know how to differentiate this type of function from, for example, an exponential function. So you would know that a 2 to the power of b is an exponential function, while an x to the power of n will be a polynomial. You would need to know how to describe the end behavior of many polynomial functions. So for example, you could talk about how the function behaves as x approaches something, so positive infinity or negative infinity. But you can also describe the behavior using quadrants, for example, from quadrant 3 to quadrant 1. You could also talk about finite differences, because remember, a polynomial function will always have a finite difference, which would be found by this here. Remember, this is your leading coefficient times the factorial of the highest order, or the highest degree, I should say. When we're talking about polynomial functions, we'll also need to remember how to find whether or not something is even or odd. So if the function is even, f of negative x should equal to f of x. If the function is odd, then f of negative x should equal to negative f of x. As for every chapter we've covered, we need to know how to apply transformations to a polynomial function. In this case, we actually are going to be talking about just a single power, so x to the power of something, and the transformations that we can apply to that. You should not be expecting the transformation of, for example, a third degree. You could talk about how to factor it and graph it that way, but it won't be in this format, which is why I didn't put it here. Lastly, perhaps the most important topic that you need to know, which is really useful in calculus, is of course rate of change. You need to remember that rate of change is simply found by delta y over delta x, which is just the difference between the 2 coordinates. Again, if you want to talk about rate of change, we need to know the difference between AROC and IROC. AROC, which was average rate of change, is found between 2 points. However, IROC is the instantaneous rate of change, and it is found at only 1 point. The way we do this in advanced functions is by selecting a very close value for x1. So that value could differ by perhaps like 1,000th of a unit. If you understood those concepts from chapter 1, we can actually start talking about chapter 2. So in chapter 2, we have learned a lot of different material. Most of it was new equations used to express key concepts and key points of a graph. So the very first thing that we've learned is how to divide a polynomial by a binomial. And we learned that we could write it as a quotient with a remainder. So if we divide p of x by x minus b, we actually get p of x is equals to x minus b times the quotient plus the remainder. If you want to write the actual form of what p of x is divided by x minus b is equals to, you would simply say that that is the sum of the quotient and the remainder divided by x minus b. Again, the reason why you would know this is, for example, if you were asked to write something in quotient form, you would choose the appropriate one. Next, we talked about the different theorems. The first one would be the remainder theorem, which states that p of x divided by x minus b has the remainder p of b, and p of x divided by a of x minus b has the remainder of p of b divided by a. The factor theorem actually told us that if x minus b is a factor of p of x, then p of b is equals to 0. If a times x minus b is a factor of p of x, then p of b divided by a should also equal to 0. The integral zero theorem and the rational zero theorem are very similar, because the integral zero theorem states that if x minus b is a factor of p of x with the leading coefficient 1 and the remaining coefficients that are integers, then b is a factor of the constant term of p of x. All that is saying is that if x minus b divides p of x perfectly, then b is a factor. The same thing goes for the rational zero theorem, but now instead of having x minus b, we would actually have ax minus b, and that would tell us that if p of x has the integer coefficients and x is equals to b over a is a rational zero of p of x, which means it actually exists and we can find it, it won't be like square root of 3 over 2, then b is a factor of the constant term of p of x. A is a factor of the leading coefficient, and ax minus b is a factor of p of x. Again, in simple terms, if x is equals to b over a is a factor, then a has to be a factor of the leading coefficient, b has to be a factor of the constant term, which would be the last term of your polynomial. If you understood all of that, the next thing you have to know is what a family of polynomial function looks like. Again, a family of polynomial functions are simply functions that have the same zeros. So those could be a1, a2, a3, all the way to an. There can only be n zeros for any type of function. So if you have a third degree function, you'd only have at maximum 3 zeros. Again, the way that we would express a family of polynomial functions is by finding those zeros and putting a constant term beside it. This would be your stretch or compression factor. Again, k could be any real value besides 0, because if it's 0, you just get y is equals to 0. That's not really helping anybody out. So then, if you understood that and remember how to do that, we need to remember how to factor inequalities. So if they can be factorable, then we could solve them algebraically by making interval charts and by using those factors that we found. Again, the intervals for these interval charts could be found using the zeros of the function, and the way you would find the zero of the function is by either using the integral zero theorem or the rational zero theorem. However, if the function is not factorable, the only way you could solve it is by using technology. So you get a graphing calculator, you'd plug it in, then you'll see where those zeros are. You could also, from just the graph, tell where it's greater than 0 or less than 0. But that won't be on your exam because nobody can really test that. However, I guess if you are doing online this year, that might be a possibility. But either way, it's very simple to do. Now let's talk about chapter 3. So in chapter 3, we actually learned rational functions. We learned about 3 main types. The first one was just 1 over a linear function. When we have this kind of form, we know that c over k would be the vertical asymptote. We know that if k is greater than 0, then the first branch, which would be our left branch, would have a negative and decreasing slope, and the right branch has a negative and increasing slope. If k was less than 0, then it would have a positive increasing slope, and the right branch would have a positive and decreasing slope. The way you would know this is by just, for example, if you forgot, you would sketch a simple graph like that. I personally like to just sketch a rational function. You should by now remember what it looks like, and then if you think about how it acts besides the asymptote, which would be down here, you'd be like, yeah, this right branch is approaching it, the asymptote, which means increasing. From this side, it is decreasing, and then the negatives and positive just come from where it's positioned, like from left to right. So this way would be the first branch would be negative, and this branch would also go down, which would also be negative. Similarly, if we were to flip it over, then we would have the opposite be true. We would have a positive increasing slope at first, and then a positive decreasing slope later on. The second type of function or rational function we talked about was 1 over a quadratic. So here things got a little bit more complicated. As you may recall, we actually were getting either 2, 1, or 0 asymptotes, but all those asymptotes came from the factors of the denominator. So if that quadratic function could be factored, it would have 2 or 1 asymptotes. The factors could be found either by applying, for example, the difference of squares. You could find it using like perfect squares, or sometimes the quadratic formula. If you had 1 root, you would have a perfect square. However, we also had questions where we would have no roots whatsoever, which would mean that we have no vertical asymptotes. You'll have to keep this in mind while doing any work with rational functions on your final evaluation. Just make sure you check whether or not there are asymptotes present. Once you find these asymptotes, you can actually talk about the shape of this function. So again, you could analyze the behavior of each branch by just looking how it behaves besides the asymptotes and as it approaches positive, negative, infinity. Also, if you have 2 asymptotes, that would mean you have a middle branch, and that middle branch would have its vertex in the middle of the 2 asymptotes. Again, I don't think your teachers will provide you anything that wouldn't have it in the middle. We have looked at cases like that in chapter 3, so if you want to go back to that, I'll explain more thoroughly why that wouldn't occur. But unless your teachers are sadists, I do not believe they will put that there, because that was not covered in my school whatsoever. The last type of function that we have is of the following format: ax plus b divided by cx over d. This format is pretty easy to understand. Remember, we've learned 4 different formulas for finding out all of the key points that you will need. So those formulas are that the VA is found at d over c, the horizontal asymptote is found at a over c, the y-intercept is found by dividing b over d, and the x-intercept is found by b over a. If you remember those 4 formulas, you should be well off finding the formula for each of these if you were given those values. You should also be able to graph these functions with no problem. Continuing the topic of rational functions, we will actually need to remember what an oblique asymptote is. An oblique asymptote happens whenever the degree of the numerator is greater than the degree of the denominator. In grade 12, we will only be discussing when the degree is larger by 1. So for example, x squared over x. However, it is quite possible to have oblique asymptotes that are of different shapes rather than like a completely straight line. The only thing you need to know for now is that to find the equation for this asymptote, you'd have to do long division and find the quotient. We will not be dealing with what the remainder represents in this case. Now that we're on to the last two topics, they're pretty much intertwined. The first one is talking about rational equations, and in order to solve them, you need to factor, you need to move all of the variables to one side, so you have a 0 on one of the sides left. Then you'll need to state your restrictions. After you do that, you would need to find the lowest common denominator and rewrite the inequality. Again, what you would do is you would multiply everything by the value of the lowest common denominator divided by itself, which would actually just multiply everything by 1, but it would also rewrite the inequality in a way that allows us to work with it and have the ability to simplify it further. Once you simplify, you might be able to factor again. And after that, if you got all of your factors, you can solve. Again, remember, to solve a rational equation, all you need to do is find the zeros. So if you could find all of the factors, finding the zeros is just making those little factors equal to 0. When it comes to solving rational inequalities, you start with the same process. You go all the way to here, but now, instead of making everything equal to 0 and saying that's it, you're gonna make those zeros and you're gonna create an interval chart, just like we did with polynomial functions, and then figure out whether or not your function is greater than 0 or less than 0, or if it's greater or equal to or less than equal to 0. Again, it's very important that you remember your restrictions in this step, because if you have a question that says greater or equal to 0 and you find a vertical asymptote at that certain point, you know you can't include that vertical asymptote, as that would not be a value the function can reach. So if you understand all of those concepts, we can now talk about chapter 4. Chapter 4 is the beginning of trigonometry. So this chapter is a lot of algebra, which is why you can see a lot of equations. If you remember all of these equations, you should be well off. Again, these equations include talking about how radians are related to the arc of an angle, or sorry, arc of a circle, and the radius. You'll need to know how to convert from radians to degrees, which is multiplied by 180 over pi, and then you'll need to know how to convert from degrees to radians, which is pi over 180. You'll need to know your CAS rule from grade 10. You'll need to know your special angles, which are 0, pi over 6, pi over 4, pi over 3, sometimes pi over 2, it's good to know. For all of the trigonometric ratios, which include sine, cosine, tangent, cotangent, cosine, and cosecant, and secant. If you remember all of these, you'll need to know these equations here so that you can start and actually solve and prove trigonometric identities. So you'll need to know the compound angle formulas for sine, cosine, and tangent. Remember, the compound angles could be for a plus b and a minus b. You'll need to know all of these different formats because either one of them could be used, for example, to solve an identity. You also need to know your basic Pythagorean identities, which would be the ones we've been dealing with since grade 11. So sine squared root of x plus cos squared root of x is equals to 1. These two are more rarely used, but they can still be applied in certain situations. Then, as I've talked about before, sometimes you'll be given a double angle, in which case we could use the double angle formulas, which are listed over here, to solve for those. So we've actually gone through the derivation of all of these different formulas, except for the probably these ones here, so 1 plus tan squared of x and 1 plus cotangent squared of x, but that shouldn't be a big deal because usually the derivations could come in form of a thinking assignment rather than a communication question on an exam. However, if you really feel like you want to study how to do that, I'll link the video down in the description in case you want to watch that. Now that you know all of those formulas and can now easily solve trigonometric identities, which just means that they're all possible values for an identity are met, so for every value of x, the identity will hold true, we can talk about the trigonometric functions as part of chapter 5. So for chapter 5, you'll need to remember the graphs of sine of x, cos of x, tan of x, cosecant of x, secant of x, and cotangent of x. That sounds like a lot until you remember, oh yeah, sine and cosine, same thing, but just with a phase shift. Cosecant and secant, same thing, but just with a phase shift. Oh, tangent and cotangent reflected with a translation. Again, it shouldn't be that hard. We've done a lot of work on these. You've done twice the work if you've been following these videos and also actually studying this in school. So by now, these graphs are imprinted in your brain. Whether you like it or not, they're stuck in there, or hopefully by now they are. Again, the most important thing you need to know is that they're all periodic. If by now you don't remember that, you really need to step up your game. Like, I'm not trying to be mean, but if you're going into the advanced functions exam and you don't know that these functions are periodic, you really need to study harder. When we're talking about the transformations of these graphs, we use the same general form as we've been using for all the other functions, which is, of course, using our a, k, d, and c values. In this case, it's a little bit different because these values actually represent something, not only just stretches and reflections and translations, but actually the absolute value of a would be the amplitude. D would be referred as the phase shift rather than translation. C is still the thing we know and love, that's just the vertical translation of the graph. But the k value can actually be used to find the period of the function, which would be 2 pi over k. The k value could also be referred to as the stretch and compression horizontally, but most likely you won't be using it that way. However, if you wanted to, you still can. Just make sure it fits the period provided by this equation. If you know how to graph all of these and apply the transformations for all of them, we didn't really do tan and cotangent that much with these translations because, for example, the amplitude gets a little bit ridiculous since the amplitude for tangent and cotangent doesn't actually exist. But yeah, if you're good with that, we can actually start talking about the trigonometric equations. So it's essential for you to know that some of them will not have solutions. Your teachers may be trying to trick you. They'll be like, okay, when is sine of x equals to 2? And you'll be like, that's impossible because sine of x has a range of -1 to 1. And that's how you get full marks, kiddos. If that isn't the case, if your teacher is trying to actually test your concepts and knowledge of this chapter, you'll have to remember that since these ratios are periodic, you could have infinite amount of answers, which is why you should always pay attention to the period and the intervals provided in the question. So if it says to solve it from -2 pi to 2 pi, do not go over that or below that. Again, if you're given a trigonometric equation and it has some angle, like a double angle, for example, you can always express it using another variable. So here I said, hey, let y equal to 2 of x. So now, for example, cos of 2x could be cos of y. This will allow you to more simply visualize these type of ratios. You can also say, instead of saying y is equals to 2x, say y is equals to cos of 2x. And then you could, for example, get a quadratic formula, which you could solve for the roots super easily. Whichever way you do it, you need to be aware that the domain changes. So in this case, y is equals to 2x, this domain would actually have to increase by 2. So if it was 2 pi, it would now be 4 pi. So you'd be solving for those values. And then once you revert back to cos of 2x, you would have to divide all the values you found by 2. Again, this would just be a linear relationship. If the domain increases by 2, divide your answers by 2. If it increased by 0.5, divide your answers by 0.5. It's also important, again, like I've mentioned before, if you're given a quadratic, factor it. There's no other way you could do it. Don't try to graph it. That would be pretty difficult for what we know right now about these functions. So just factor it. If it can't be factored, that means it has no answers. So now let's actually talk about chapter 6. In chapter 6, we started talking about exponential and logarithmic functions. First, we talked about a really simple exponential function. Here we learned its key characteristics. The first one being the fact that it has a repeating pattern of finite differences. So we can no longer find what its finite differences are, like we could for polynomial functions. We also learned that a rate of change that is increasing proportional to the function for b greater than 1 exists, again, if b is greater than 1. It would be increasing proportionally. If it was between 0 and 1, then it would be decreasing proportionally. If we wanted to talk about the domain of the function, the domain would be x is an element of all real numbers. The range would be y is an element of all real numbers and greater than 0. It would have a y-intercept of 1 and a horizontal asymptote at y equals to 0. We also talked about how we got these values back in chapter 6, so if you want to go watch that, I'd highly encourage it, but it isn't necessary if you remember just what these values are. Next, we've learned that the logarithmic function is actually the inverse of the exponential function, and we've got the relationship. If we had y is equals to log of base b of x, that is the same thing as x is equals to b to the power of y. If we wanted to find the value of 1, for example, of x, we could use either one of these givens to find that out. We've learned that exponential and logarithmic functions are only defined for positive values of the base that are not equal to 1. So you cannot have b equals to negative 4. You can't have b equals to 1, because if b is equals to 1, then it would produce an infinite amount of solutions, which would be not a function. Remember, if we have more than one y value for an x value, that is no longer a function. We also need to know how to transform the logarithmic graph, again using the same type of characteristics we used before. So our a, k, d, and c values, again, a is vertical stretch or compression, k is horizontal stretch or compression, d is your horizontal translation, and c is your vertical translation. If you don't remember those, you really need to practice. You really need to practice. The last two things we learned was actually the power law and the change of base law. These are very useful actually in chapter 7, when you'll be talking about changing and solving logarithmic and exponential equations, but we did cover them in chapter 6, so here they are. Remember, the power law simply states if we have x to the power of n as part of a logarithm, we could simply take that power and plop it as a multiple. So log of base b of x to the power of n is simply n times log of base b of x. This will hold true as long as b is greater than 0, b cannot equal to 1, x has to be greater than 0, and n has to be a real number. It has to be an element of all real numbers, right? Because if it's not a real number, then we would have an imaginary number, and that would not be something that we have worked with before. Lastly, we have our change of base formula, which simply states that if we have log of b of m, we can write that as the division between log of m and log of b. So again, remember base has to be greater than 1 essentially. So that's what this says, and m has to be greater than 0 because like solving for 0 cannot occur. Like log of 0 does not give us anything. So now that we are done with that, we need to actually talk about the 5 other formulas we've encountered throughout this chapter. Some of them were actually part of chapter 7. However, I thought it would be much more beneficial for us to talk about all of them at once rather than split it up into chapters 6 and 7. So here they are. The first one is the pH scale, which is equals to negative log of the hydronium ion concentration. Again, this is really simple because you won't be actually given, or you won't have to actually know what this means. It'd be like, okay, here is the concentration. What is its pH? And you just plop that number in here and you'd be like, oh yes, it is actually 3. The next formula we need to know is the magnitude of an earthquake, which is found by this formula here. This is our basic earthquake, the most basic you could find. And then this is the one that we're comparing it to. You could also use the similar format of this, where you have one earthquake compared to another, because these types of question will always be a comparison. It will be like, hey, this earthquake produces this much damage, and the second one only produces this much. How much stronger is this earthquake compared to the other? And you'll be like, oh, put these numbers into here, find the log of that, and you'll be like, oh, the second earthquake is actually 100 times stronger. So if you were in that earthquake, you'd be dead. So yeah, that's the kind of things you'll be doing. For the third equation, we're actually talking about sound levels. Here, it's a direct comparison between sound 1 and sound 2. So the I2 and I1 are actually the intensities of the two sounds in watts per square meter. I do not recall actually like how much our teachers cared about us using this exact unit, because again, it's just talking about the difference in the decibel values. You could also talk about how strong one compared is to the other. For questions like this, you'd have to be given the values. You'd, for example, be given 100 decibels and 62 decibels, and you'll have to find the ratio of their intensities to say how much one is stronger than the other. If you're not given the decibels, you have a problem because you can no longer find these values here, and so you can't solve the question. The second last equation we've dealt with was actually growth and decay. We've learned about this one in grade 11. It is defined as f of x is equals to a times b to the power of t over h, where a is the initial amount, f of x is the final amount, b is 1 plus minus the growth rate or the decay, depending if it's the plus or the minus. T would be given as the number of growth or decay, and h would be the period of time in years. So you'll be, for example, given all of these but one, and it'll be asking you to solve it. You'd be like, okay, if the final amount is 10, we don't know a, but we know the other 3. What is a? Plop in the numbers. You might have to take the logarithm of it to find the answer, but that's nothing we haven't dealt with before. The last formula that we need to know is the compound interest formula, where a is equals to p times 1 plus 1 over n, and that all is to the power of n times t. Sounds complicated, but again, we've been working with this for the last 2 years, so you should be familiar with how it works. In case you're not or have forgotten a little bit, a is the future amount, p is the present value, I is the interest rate per compounding period, n is the number of compounding periods per year, and t is the number of years. So using those values, you'll for example be asked to solve for one of them. Usually it is the future amount or the present value. Sometimes it could be t. It's really rare for you to have to solve for I or n because they're used twice, but either way, if you don't see them, that means like you just have to do an extra amount of work. As a quick note, I just noticed that it said 1 instead of I here, so again, I'll be posting a Word document with all of these written out instead of like a PowerPoint, so you can just print it out in case you just want to memorize everything that's on it. That typo was fixed there, and so I just wanted to let you know about that. Moving on, we have chapter 7, which is more or less just chapter 6 with more algebra with it. So what you're covering in chapter 7 is simply solving exponential equations. Again, that could be done in 2 or 3 different ways, depending whether or not you have a graphing calculator available. The first way would be to change the base to the same value using the power rule. If the base is the same, that means that the powers should be the same, and if the powers are the same, it's much easier to solve for. You could also take the common logarithm from both sides and then use the power law. If you take the common logarithm of both sides, you can then transform it back into, for example, a more simplified exponential equation. Again, what you're working for is to equate those powers. So if the bases are different, you can change the base. You can find the common logarithm and use the change of base formula, for example, but still your key goal is to get those powers to equal to the same thing. Again, you'll be solving for power. You'll be solving for x. If a quadratic equation is obtained at any point during those two procedures, you could always factor it if it's like a difference of squares or a perfect square, but you could also use the quadratic formula. As the case with exponential and logarithmic equations, you have to watch out for extraneous roots. Extraneous roots are the values for which the solution is not valid. So for example, we know we can't take the logarithm of a negative number. So, we can't take the logarithm of a base of a negative number, so that shouldn't work out. We also can't have a negative value or like the square root of a negative value. So if that ever happens, that's an extraneous root. Once you do that, we will actually be moving on to the last 2 laws of logarithms that we need to know before starting to solve logarithmic equations. So those 2 laws is the product law and the quotient law. So the first law we need to talk about is the product law. The product law simply states that if you're taking the logarithm of 2 values multiplied by one another, that is equal to the sum of the individual logarithms. Again, in this case, b has to be greater than 1 essentially, m has to be greater than 0, and n has to be greater than 0. The quotient law actually says that if you have a logarithm of a number divided by another value, then you'd actually equate that to the logarithm difference between the two. So it'd be log of base b of m minus log b of n. Again, the restrictions are exactly the same as for the product law. If you know everything up to now, you should be more than welcome and have the ability to solve logarithmic equations. So at first, you could try to solve these logarithms by expressing them as the logarithm of the same base, because we know if a is equals to b, then log of a should equals to log of b. This is like taking the common logarithm of both sides. So if you take the log of the same base of a number and those actually do equate, then you could prove that a is equals to b. You could also always try to convert logarithmic equations into exponential equations. With this, you can apply several factoring techniques that you've learned before. Also, do not forget about the buddies we've learned here, so the product law and the quotient law, they might be able to apply. You could also, for example, try to apply any of the formulas we've learned here. So the power law would probably be used a lot. The change of base law could be really useful if you're trying to equate them to the same logarithm of the same base. With that being said, we can now move on to the last chapter of advanced functions. So the last chapter of advanced functions was actually teaching us how to combine different functions together. So the first thing we've learned was the superposition principle, which stated that the sum of two or more functions can be found by adding their ordinates, which would be the y coordinates of the function, to their x coordinates. We've learned that the sum or difference of those functions would equal or would have the domain common to the component function. So it would only be defined for the domain that is present in all of the components. We've also learned about the product and the quotient functions, which are defined as y is equals to f of x times g of x and y equals to f of x divided by g of x respectively. Again, their domain has to be common to both original functions, and the quotient function is further restricted so that a g of x cannot equal to 0. Because again, if it were equal to 0, it would be dividing by 0, which is a pretty impossible thing for us mathematicians. If you remember how to do that, you could also apply the superposition principle pretty much. Like again, if you were to multiply a value by another value, that's like stretching it. Like you could always try that to plot these graphs. Next thing we learned was actually the composite function. So for example, f of g of x, like we have here, or maybe g of f of x. We've learned what this actually means is that g of x was actually substituted in for the value of x in f of x. We've also learned that this is a different way to write it, so if you ever see this type of format, remember it's the same thing as this over here. Again, if you were trying to determine an equation for a composite function, you would simply substitute the second function into the first, as read from left to right. So to determine f of g of x, substitute g of x for x in f of x. That's a lot of x's, by the way. If you were ever trying to evaluate a composite function, f of g of x, at a specific point, you would do it in two possible ways. You would first of all try to substitute the value into the equation of the composite function and then simplify it and solve, or you could evaluate it at g of x and then take that value and substitute it into f of x. Each way has its own benefits. I personally like to do evaluating g of x separately and then f of x because it lets me see all those different steps to make sure that I'm doing it right. Because sometimes if you mess up in the formation of the composite function, your answer will be completely wrong. So you would not want that to happen. So now that we're coming to an end, we're actually going to talk about solving inequalities of combined functions. The way you could do this is by graphing both functions on the same set of axes. You could then also, for example, graph f of x minus g of x such that it's greater than 0. If it is greater than 0, that means that f of x is greater than g of x. If it is actually less than 0, then g of x would be greater than f of x. You could also graph the quotient between f of x and g of x when it is greater than 1. If it is greater than 1, then f of x is greater. If it's less than 1, then g of x is greater. Again, each of these have their own benefits and drawbacks. For example, if the functions are complex, it would be pretty difficult for you to sketch them on the same set of axes. However, if your function has a lot of negatives and positive components, sometimes taking the ratio of it will not give you the right answer without some analyzation of the graphs. So you would have to do a little bit of thinking before choosing the appropriate method for graphing these inequalities. Lastly, if we were to talk about how to develop the model consisting of a combined function, so this would be, for example, if you're talking about something to do with sciences, like how a bacteria grows per year. Like that could perhaps be a combination of exponential and trigonometric functions. So what you would have to do is you would have to identify the functions that go into it. So if you see something that looks like it's going up and down and like periodically but not quite, you also see that it is increasing really fast, that would give you an idea that you're dealing with exponents and trig. You can also identify the nature of the rate of change. Again, this would be defined by like the steepness, for example, of those curves. If something is going very slowly, it could be a linear function. If something just went from like really low numbers to like really large numbers in a matter of like 2 x values, perhaps you have a polynomial function that you're dealing with. Either way, this will be really easy to see in a question. Again, usually it'll give you little hints about how those graphs should look. Of course, you would also have to consider the other key features of graphs, or the equations that would fit the given scenario. Again, if you're talking about merry-go-round, we know that that has a certain cycle that it follows, so that could be trigonometric. If we're talking about, for example, roller coaster, that could represent a graph of a polynomial function. Each of those, we know how to find its key points. For example, zeros. It could also have like asymptotes if you're having rational functions involved. If you're dividing a function by a function, knowing the asymptotes would be really important, because then you would know where the function is defined and not defined. Combining all these topics could seem a little bit difficult, but again, if you did all of the chapter 8 practice, you should be good. With that being said, we have actually reached the last topic of advanced functions. Hopefully, everything I've stated here you've already learned, or at least familiarized yourself with. I have published a video on every topic that I've covered in this video, so if you have any questions, you could go back to those videos and look at them. I've actually color-coded every chapter, so for example, yellow would be chapter 6, so wherever you see a yellow thumbnail, that would mean that is chapter 6 content. Again, if you have questions or if you're uncertain about something, you could email me, you could leave a comment down below. If you want a one-on-one session, again, just try to contact me. Perhaps I could set that up and try to help you out. Hopefully by now you have enjoyed the advanced functions course. I'm really hoping that everybody who watched this video gets at least like 90%. I know that's really wishful thinking, but I believe in you guys. If you actually stayed here and persevered, you deserve nothing less. So I just want to say congratulations on finishing the course. Hopefully we will start calculus and vectors soon. So bye guys!